So thanks for allowing me to talk here today. We're going to talk about ICs and in particular photodesorption and photo processing from CO2 ICs. It's a part of my work as I'm a third year PhD student at Paris, and I will focus on flux and fluence effect. So I'm interested in molecules in the interstellar media, and in particular in cold region where the temperature are around 10K, like in protoplanetary disk, dense cores, or PDLs, where you can find small molecules like water, CO, CO2, or more complex molecules like methanol or H2CO, like right here, or you can find high gas phase abundances in cold region. And non-thermal desorption has been a key, a huge vector to explain those high gas phase abundances. So as you know, in this media, molecules are going to stick on this grain, and non-thermal distortion is a huge path to explain the high gas phase abundances, so the transition between the solid phase to the gas phase. So I focus on non-thermal desorption and on photon-induced desorption in the energy range of the vacuum ultraviolet. This has been a huge subject which has motivated a lot of laboratory experiments in the last year. So why are we studying CO2? It's because it's third abundances in the interstellar medium solid ices, and one of the main components of ice in cloud, depending on where you are after or before the CO freeze out. There have been a lot of studies those last decades showing up different photodisruption yield and also evocated different mechanisms occurring during the photodisruption. And the two main possible ways for CO2 desorption, which are evocated, are firstly the desorption induced by electronic transfer, called diet, in which we have an electronic transfer which leads to the desorption of CO2. And it's a mechanism who depends on ice composition and which is independent from the photon flux, as it's a single photon process. The other process evocated is a photochemistry process, which is a process which is flux dependent, as you create more radical in the ice, and which leads to the desorption of CO2. So here the question is to investigate the flux, as it allows us to distinguish between those different mechanisms. So how do we proceed now? We have a new HV chamber called SPICE at MONARIS that we can move on to the Desir beamline output at the Synchrotron Soleil facility. On it, we have a gold substrate that is cooled down to 15K, and we're gonna grow molecular ice of CO2 of a few monolayer. We can probe the flux of molecules, the number of molecules which are desorbing, with a quadrupolar mass spectrometer, and we can probe the ice bulk to see the chemical evolution of the bulk with infrared spectroscopy. The advantages of using the DZR VUV beamline is that they provide us a continuous flux of photon, which is fully tunable in energy and in flux. With that, we can obtain photodisruption yield, but also study the behavior occurring during the desorption of the molecule, and in particular, the flux and the fluence effect. So here are the flux results. Those is directly the signal of the quadrupolar mass spectrometer that we derive to obtain the photodisruption yield as a function of the fluence, which is the total amount of photon that the ice receive. Those are the experiments performed at 1 photon energy and a flux which is quite high, out of the magnitude of 10 to the power 14 photons second centimeter square. So here you can clearly see the three main species desorbing, CO2, CO, and O2. And there is obviously two different behavior with CO, which have a fast buildup right here, which tends to slowly decrease, and CO and O2 who increase slowly until steady state is reached. So here we clearly have two different behavior in the desorption dynamics, and this could be a sign of two different mechanisms occurring in the desorption, so one for CO2 and one for CO and O2. So as I told you, flux is an important parameter. So we perform experiment at different flux condition. as I show you here. So the spectra before is the high photon flux in red. And for your comparison, the left part is a low fluence part, and the right part is a high fluence. So if you want to represent the low flux experiment in a dotted green here on the right spectra, it would be a quick line, a few line of dot right at the beginning. So here you can see, firstly, that we have the lower desorption, lower flux used lead to the higher desorption rate for CO and O2. You must notice that for CO2, that's not especially the case because the error bars are really big. So we do not see any flux dependencies for CO2. That's for the low fluence regime. For the high fluence regime, it's the opposite phenomena that we see, with the higher flux used lead to the higher desorption yield for CO and O2. So that reinforces the fact that two different mechanisms must be occurring in the desorption of CO and O2, and one other mechanisms for CO2. So we try to quantify those desorption dynamics in order to obtain evolution cross-section of the system that I show you right here on the table. And the first things to notice is that the evolution cross-section are higher for CO and O2 than for CO2. Evolution cross-section for CO and O2 are flux dependent, as there is an order of magnitude between the lower flux experiment right here and the higher flux experiment. That's a fact that we do not see for the evolution cross-section of CO2, because all of them are at the order of magnitude of 10 to the power minus 18. So we can conclude as this that different mechanisms must be occurring for CO2 and for CO and O2 on the other end. That's for the molecules which are ejecting from the surface. We inspect the ice bulk, so we perform infrared spectroscopy. So here you can see the spectra before and after irradiation in red, in blue. And you can see bands attributed to CO2 with the combination mode band here, the stretching mode of the CO2 right here, the stretching mode of the isotopologue 13, and the bending mode. The two other bands are attributed to CO, that we can see a zoom here and it present here, and CO3. I will focus first on the CO2 stretching mode that you can saw here. And we perform the different spectra, and you can clearly see that during the irradiation, there is two different parts. One is decreasing, one is growing. The band is kind of complicated to analyze, and we want to know what is this growing part. And we perform a further experiment with a new ICs of phase containing CO and CO2. And this could explain this peak right here. But the multi-component character of this band don't allow us to really characterize the chemical evolution of the band. So for us, the CO2, we make the hypothesis that CO2 stretching mode cannot be used to quantitatively analyze the desorption of CO2. So we focus on CO that we consider to be a good marker of the chemical evolution of the bulk, as the band is only growing during the irradiation. So we take the integrated absorbance that we plot as the function of the fluence, and we try to quantify as the same way of the mass data that we obtained before to have evolution cross-section, this time for the chemistry. And we have evolution cross-section in the order of magnitude of 10 to the power minus 18, which, if you remember well, it's the same order of magnitude of the desorption of CO2. So here you clearly have a great correlation between the desorption of CO2 and the chemical evolution of the bulk. And I told you before that there is a process known for of this character, is the desorption induced by electronic transfer, as it depends on the chemical bulk composition and involve several molecular layers. So when you are at low fluence, the energetic transfer will occur in a fully CO2 solid, but as long you have more photon and the fluence is higher, the glass will progressively evolve to a mix of CO, CO2, and O2. and the electric energetic transfer will occur in it, changing so the behavior, the dynamics of this option. If you look back to the evolution cross-section for CO and O2, you see that the evolution cross-section are higher. This means that the process occurring in the desorption need less photons to occur. The process is faster, in other words. So that refer to a process which occur at the surface of the ice and a chemistry surface process. So at low flux, the surface density of oxygen will be lower, and the atomic oxygen will combine with CO2 to lead to the ejection from the surface of CO and O2. When you increase the flux, the local density of atomic oxygen will increase, and the atomic oxygen can react with CO and with another atomic oxygen. So to conclude, we have a great correlation between the ice vibrational spectroscopy and the desorption dynamics. And our flux and fluence experiments allow us to explain the variability that we observe in the photodesorption yield and in the mechanisms evocated in the literature. And we are now able to distinguish between different processes occurring in the desorption. So with the desorption induced by electronic transfer process for the CO2 desorption, and from surface chemistry, which occur in the desorption of CO and O2. So as you know now that the photochemical process depend on the flux, how can we extrapolate laboratory experiments, which are made at high flux, like 10 to the power 14 or sometimes 16 in the lab, to the interstellar condition where the flux are in the order of magnitude to 10 to the power of 8, 5. So really systematic flux dependency study is required to distinguish between the mechanisms and obtain the yields. Other fact that I forgot is that we do not observe any crystallization during the irradiation of our ice sample. I would like to acknowledge organizer to allow me to talk here today, every fundings we have to perform experiments, and colleague at the lab, and of course you for your attention.